Hello everyone, my name is Delphin Sénizergues and this is my contribution for the One World Symposium of 2020. I'm going to talk about the height and profile of weighted recursive trees. So first, let us explain what weighted recursive trees are. So we start with the sequence Wn of non-negative numbers that we call weights, and we're going to construct a sequence of trees by adding vertices one at a time. We start with a tree at time 1 with only one vertex labeled 1, and at each step of the construction we add a vertex to the tree. So at time n plus 1, the vertex labeled n plus 1 is added to the tree, and it chooses its parent at random among the n possible vertices that are already present. And it does so with priority proportional to the weights of those vertices. So the probability of attaching to any vertex k is proportional to wk. So actually we can rewrite this probability of attaching to vertex k as wk divided by the sum of the weights of the n first vertices, which we denote by capital Wn. So we say that the tree Tn, obtained after n steps of this construction, is a weighted recursive tree of size n with sequence of weights w. Our goal is to study the asymptotic behavior of some statistics of the tree Tn when n is large. In this talk, I will mainly focus on the height and the profile of the tree. So first, let us mention that if the sequence of weights Wn is constant, then Tn is known as the uniform recursive tree, which has been studied since the 70s and for which precise results have been proved. We are going to work under the assumption that capital Wn, the cumulated weight of the n first vertices, behaves roughly like a power of n to the gamma, for some positive constant gamma. There are, in fact, additional technical assumptions that I will not discuss here, which ensure that the sequence Wn is sufficiently regular in some sense. One motivation for studying this is the relation of this model to the affine preferential attachment trees, for which the construction is similar to that of the weighted recursive tree, but in which the attractivity of a vertex is linearly reinforced by its degree. And the distribution of those growing trees, so the affine preferential attachment trees, can be shown to be that of a weighted recursive tree, but with a random sequence of weight w that satisfies our assumption for some gamma between 0 and 1. Let us also mention that this type of questions about the weighted recursive trees appears naturally in the study of a process called the monkey walk, studied by Meyer and Uribe Brabo. So let us describe those results. So first, let us recall some definitions. So the height of a vertex is its distance to the root, which is here the vertex label 1. And the height of the tree is the maximal height attained by a vertex in the tree. Then the profile of the tree Tn is the function that we call Ln that associates to each integer k the number of vertices of Tn that are exactly at height k. In order to picture this function, I will represent it as a histogram where the length of the red bars correspond to the number of vertices at the tree at each height. Okay, so a first result is that almost surely the profile has a Gaussian shape centered around the value gamma log n with variance gamma log n. So it means that most vertices of the tree are in a window of size roughly square root n around the value gamma log n. Then we might wonder what happens at other heights. And indeed, what we get is that if we plot the profile, but now on a log scale, then we can asymptotically see some limit shape. So indeed, if we consider a height of order gamma exponential z log n, then the number of vertices at that height is asymptotically n to some exponent f gamma of z, where f gamma of z is defined by the following formula. So of course this only makes sense if the value of f gamma of z is positive. And it turns out that if we denote by z plus the unique positive zero of f gamma, then the value gamma exponential z plus log n is the right asymptotic for the height of the tree Tn. Okay, so I summarized these results in the following theorem. So under some assumptions on the sequence of weights that depends on some parameter gamma, the following statements 1, 2, and 3 hold almost surely as n tends to infinity. So assertion 1. Assertion 1 is the convergence of the profile to a Gaussian shape centered around gamma log n. Assertion 2 is gives the asymptotic of the number of vertices at height gamma exponential log n, exponential z log n for z in some range. And finally 3 gives us the asymptotic equivalent for the height of Tn. In a work in preparation with Michel Pin, we study the asymptotic behavior of the height in more details, and we obtain the following correction terms in probability with a term in -3 over 2z plus log n plus a tight term. So note that Michel talks about our work in this very conference, so I strongly encourage you to go watch his talk. Okay, so in the next minutes I'm going to present a very useful construction associated to weighted recursive trees, which should be enough to give you an idea of why assertion 1 should be true, but also give you a good starting point for proving the other assertions 2 and 3. So first we start with a remark. In the construction of Tn, every node k was choosing its parents among the vertices with a lower label, with probability proportional to their weight. And every time this was done independently of the shape of the rest of the tree, so in fact all those choices are jointly independent. So what this allows us to do is to discover the tree Tn by sequentially discovering the parent of the vertices, but we can do this in any order we like. So let us see how this might help us understand the height of vertices in the tree. So what we are going to do here is to discover the path from vertex 1 to vertex n in the tree, and we are trying to do that by revealing as little information on the rest of the tree as possible. So let us present a graphical example of this for n equals 5. So let us construct the path from vertex 5 to vertex 1 in a downward fashion, by successively checking for each vertex if it belongs to the path or not. We start with all the vertices that we haven't checked already in the right bin. So first we checked whether vertex 5 is attached to vertex 4. This happens with probability equal to W4, the weight of vertex 4, divided by capital W4, the sum of all the weights of the vertices 1 to 4. So let's say it's not, so I put vertex 4 in the left bin. Then, conditionally on this, I will check whether vertex 5 is attached to vertex 3. Again, this happens with probability W3, divided by the total weight of the remaining vertices, capital W3. So let us say that it works this time, and vertex 5 is attached to vertex 3. Then, where is vertex 3 attached? Well, again, it is attached to one of the remaining vertices in the right bin, and we can check them one by one. So is it attached to vertex 2? Well, this happens with probability W2 over capital W2. No, so we put it in the left bin. Now, is it attached to 1? Yes, because it's the only possibility. It happens with probability 1. And so we have just constructed the path from vertex 5 to vertex 1. So in the end, from this particular construction, we get that every vertex k will appear in the path from vertex n to vertex 1 with probability wk over capital Wk independently for all k between 1 and n minus 1. So in particular, this allows us to express the annealed distribution of the height of vertex n as a sum of independent Bernoulli random variables. So from this, it is easy to compute the expectation of the height of vertex n, which is expressed as this sum, which we can show from the assumptions on the sequence Wn that it is asymptotically close to gamma log n. So this explains why, at least in expectation, most vertices are around the height gamma log n. Then the Gaussian shape of the profile in expectation can also be easily obtained using the CLT for the height of vertex n minus its expectation. And the second assertion can also be obtained, also in expectation, by studying the Laplace transform of this random variable. Then, in order to get the corresponding almost sure results, we have to study a quenched version of this Laplace transform, which is taken conditionally on the tree at time n minus 1. And it turns out that 1 divided by the other is a martingale, and this holds for any complex value of z. So actually, for a certain range of z, the corresponding martingale converges nicely to a non-zero limit, and it allows us to use the precise results of Kablushka, Marinich, and Sulzbach to obtain our results about the profile. Thank you for your attention.